In section 8.2, we're going to continue with probability by investigating tree diagrams, tables, and sample spaces. We saw from the previous section that, and oftentimes in order to compute a probability, we need to do some counting techniques to either count the size of the sample space or to see how many elements are in our event. One of the ways that can oftentimes help us to diagram all of the different potential outcomes from a sample space is the use of what's called a tree diagram. A tree diagram is a diagram consisting of branches corresponding to the outcomes of two or more probability experiments that are done in sequence. These are oftentimes very useful when you have things that are not overly large, and they really kind of give us a good illustration of things that are happening. When constructing a tree diagram, you use branches emanating from a single point to show the outcomes of the first experiment, and then to show the outcomes from the second, with branches that emanate from each one of it, and etc. For example, we could use a tree diagram to find the sample space for the genders of 3 children in a family. So we start off with a branch point, which would correspond to the 2 possibilities for the gender of the first child. Namely, let's say just boy and girl. Once the gender of the first child has been selected, each one of those outcomes would branch off of it to display the possibilities for the gender of the second child. For example, boy, girl here, and also boy, girl there. And then corresponding to each one of those, we can have yet another series of branches to denote the gender of the third child, again, boy, girl, or for each one of them. If I trace the tree, if I wanted to figure out what would be one element of my sample space, for example, I could look at this outcome right here, which would start at the very beginning and trace it all the way down to the end. This would be the outcome of girl, boy, girl, meaning the first child was a girl, the second child was a boy, and the third child was a girl. And so if we kind of like put them all together, this would give us our sample space. Boy, 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 girl, etc. And very quickly, we can now see that there's 1, 2, 3, 4, 5, 6, 7, 8 outcomes in this experiment. Now that we have the sample space, we would actually be able to use this to do some probability calculations. Find the probability that they have at least one boy and one girl. Okay. So if I come back here, they want to have at least one of each. So this one wouldn't work. This one would. This one. All of them except the all case. So if you have to have at least one of each, that means we couldn't have all boys or all girls. So what would be left over would be these 6 out of the 8 outcomes. So the probability of having at least one of each gender would be 6 out of 8. As a fraction, simplifies to 3/4, but the probability would be 0.75. Let's suppose that a coin is flipped and then a die is rolled. Let's use a tree diagram to find the probability of getting heads on the coin and an even number on the die. So here we kind of diagram it out. Again, the first thing would be the selection of what happens on the coin. That could be either a head or a tail. That's our first branch point. Then, corresponding to each outcome from the coin, we now have our branches consisting of what could happen on the die, namely the numbers 1 through 6. So the sample space here would consist of these outcomes. I'm not going to label them all, but you'd have a head with a 1, a head with a 2, ... all the way up to a head with a 6. And then we have our tail outcomes, tail with a 1, tail with a 2, all the way up to a tail with a 6. So altogether, if we counted those, that's 12 different outcomes in that sample space. We now want to calculate what is the probability of getting a head and an even number. So if we come up here, so we have to have a head, so that means it has to be one of these outcomes, and then in addition we have to have an even number. That would include a head with a 2, a head with a 4, or a head with a 6. So we see that that event can happen 3 ways out of the total number of 12 possibilities for a probability of 0.25. So if you flip a coin and roll a die, the probability that you get a head and an even number would be about 0.25. It's between 0 and 0.5, so it wouldn't be a likely event. It'd be unlikely, but again, it could still happen. Another way to list all of the outcomes in a sample space is to do a table. We saw a table earlier when we were doing our cards. For example, we could list the card type across the top, ace, 2, 3, all the way up to jack, queen, king. And then we could also break it apart for the rows according to the suit, hearts, diamonds, spades, and clubs. If I look at one element, if I look at the 7 column with the spade row, that would correspond to the card 7 of spades. Okay. Suppose we're going to pick an ordinary card from the deck of cards. What is the probability of getting a jack? Well, keep in mind that in the deck there's 4 jacks. We have a jack of hearts, jack of diamonds, jack of clubs, and jack of spades. So there's 4 of them out of 52, which would have a probability of about 0.08. Again, if I round it to just 2 decimal places. The probability of the 6 of clubs. There is only 1 6 of clubs in the deck out of the 52 cards. 1 divided by 52 would be about 0.02. And then for the last one, if we want to calculate the probability of either getting a 3 or a diamond. Okay. So let's go up to the thing. Let's go back to our chart. So we want either a 3 or a diamond. And here you got to be a little bit careful. So if I look at all of my diamond cards, all of the diamond cards would be right here, and there's 13 of those. There is also 4 3s. However, this particular card, we got to be a little bit careful here. That 3 of diamonds would be included not only in the diamond count, but also in the count for the 3s. So really, there's going to be 13 plus 4 minus 1, or 16 of them altogether. And you can think of it as there's 13 diamonds, so we have these 13, and then you would add the 3 additional number 3s that have not been included in that count. So to my diamonds list, the only other cards we would need to include would be the 3 of hearts, 3 of spades, and 3 of clubs. So it's going to be 13 plus 3, which again is going to give us 16. So there's 16 cards in the deck that are either a 3 or a diamond. So we take 16 divided by 52, which would give us a probability of 0.69. The next thing we're going to use is the fundamental counting principle to calculate the number of outcomes for an experiment when we roll 2 6-sided die. The fundamental counting principle says that if you're going to do a sequence of events, or if you have a sequence of steps, it's the number of ways you can do the first event times the number of ways you can do the second event. We could have seen this earlier. If I go back a moment to our heads, our coin and die example, we calculated this and we listed them all, and we said that there were 12 possibilities when you flip a coin and roll a die. We also could have used the fundamental counting principle to figure out the size of the sample space as follows. If we first flip a coin, that event has 2 possible outcomes. And then in sequence, we're then going to roll a die, which has a total of 6 possible outcomes. So in sequence, the total number of outcomes when you do a coin and a die is going to be the 2 times 6, which gives us 12. Exact same outcome we got when we listed them using the tree. So what happens if we roll a die, a six-sided die twice? Well, there's going to be 6 possibilities for the first roll, and we have another 6 possibilities for the second roll, which altogether would give us a total of 36 possible outcomes when we roll 2 six-sided die. If we want to, we can build a table to illustrate this. Let's suppose, just to kind of be able to distinguish them, let's suppose that the one die is a red die and the second die is a blue die. Again, the red die could show any of the numbers 1 through 6, while simultaneously the blue die could show anything from 1 through 6 as well. And if you look at it, we do get a total of 36 possible outcomes in this sample space. Just kind of picking on, let's say maybe this outcome right here. This would be the outcome where the red die would show a 2 and the blue die would show a 6. Now that we have our sample space listed, we can find the probability that the die add to a sum of 8. Let's calculate that. So out of our 36 possibilities, how many of these outcomes would add to 8? Well, 2 plus 6 would add to 8, so that's one possibility. Also, 3 plus 5, 4 plus 4, 5 plus 3. Notice it's all of these entries kind of on this one diagonal here. These would be the ones that sum to 8. How many of them are there? Well, there's 1, 2, 3, 4, 5 of them. That's going to be 5 out of 36. And 5 divided by 36 would be approximately 0.14. What's the probability of doubles? Well, in order to get doubles, they would need to have to be the same, the 2 die. There are 6 potential ways that could happen. They could be the 1 and the 1. So both die could show a 1, or a 2, or a 3, or a 4, or a 5, or a 6. So that's going to be 6 out of 36, which would have probability 0.17. And then lastly, what about the probability that the 2 die add to a number that's less than 5? Let's go ahead and calculate that. So we would need for the die to add to less than 5. If I look at this diagonal right here, okay, notice that all of these would be the ones that add to 5. 4 plus 1, 3 plus 2, 2 plus 3, 1 plus 4. On this entry, all of them add to 5. If I go below that diagonal, any outcome that's below that diagonal is going to add to more than 5. Like, for example, this one here, 3 and 4 is 7. Or down here, 6 and 3 is 9. But the ones that are above the diagonal, these would correspond to the ones that have a sum that is less than 5. They include the outcomes 3 and 1, 2 and 1, 1 and 1, 1, 2, 2, 2, and 1, 3, right? If you add up any of those pairs, they add up to less than 5. And that's going to be 1, 2, 3, 4, 5, 6 outcomes. So the probability that it's less than 5 would be 6 out of 36, which also has probability 0.17.